All right, example 2 of 3.7, another optimization problem. And what I'm going to do in this one is I'm actually going to minimize something. So it says which points on the graph of y equal to 4 minus x squared are closest to the point 0, 2. We want closest, so that's saying we're minimizing. So we want to minimize distance. We're going to minimize our distance. Our distance formula, distance equals the square root of x minus x squared plus y minus y squared. We want to minimize our distance. Well, we know one point that we have, but we don't know another point. We don't know the closest point on that one. But we do know one point. We know 0, 2. So let's go ahead and plug 0, 2. So we know the distance equals the square root of x minus 0 squared plus y minus 2 squared. Let's go ahead and do that. Okay. So we have that so far. We need to, second step, we need to eliminate one of these variables, either an x or a y. Let's try to see what would be the simplest. I think we can go ahead and just leave it the way it is, y equal to 4 minus x squared, and that's going to, we already solved for y, so we can go ahead and plug. Here's our secondary equation right here. So we can already go ahead and plug this in for y down here. So I have d equal the square root of x squared. Let's go ahead and get rid of that 0. Plus, and now let's plug in what we need for y. So 4 minus x squared minus 2. So then, and this is squared. Okay, so we have d equals x squared plus, let's see, 4 minus 2 is 2, so we have 2 minus x squared all underneath the radical. Yep. Let's go ahead and square stuff out, expand and simplify a little bit. So on the inside we're going to have x squared plus, if you square 2, so we'll have 4. Multiply these two and double it, so minus 4x squared, then you square the last one, so plus x to the 4th, and they're all in there. And then let's combine like terms, so we'll have d equal to the square root of, let's see, x to the 4th minus 3x squared plus 4, I believe, plus 4. So there we go. We've taken our primary equation, we simplified it down into one variable, and now we need to minimize it, is what we need to do. Well, let's think about this for a second. Instead of doing a really messy derivative underneath that with that radical in there, let's think about that. If we were to minimize what's inside of the radical, so if we get the smallest possible thing we can inside the radical, we know when we take the square root of it, it's going to be even smaller. Think of this. If I have two numbers to pick from, 9 and 4. If I pick the smaller one and take the square, I'm going to get 2. If I pick the bigger one and take the square, I'm going to get 3. So obviously, if I minimize the inside and take the square, it's going to be smaller than any other number that we could pick. So let's go ahead and minimize the inside. So we're just going to take the derivative of what's inside here, and that's all we need to do. So let's take the derivative of what's inside here. Let's go 4x cubed minus 6x, I believe, right? And set that equal to 0. Well, I can pull an x out. Let's pull an x. I can pull a 2 out. So let's pull a 2x out. And we're left over with 2x squared minus 3 equal to 0. So we're going to have critical points at x equal to 0, x equal to the square root of 3/2, and x equal to the negative 3/2. So there are my critical points. Let's back this train up a little bit. What I forgot to do is look at my domain. Do I have any x's that I can't use? Well, I don't think so. I can use all negative points. I can use all positive points. So any of these are fair game. So we just need to figure out using whether the first derivative or second derivative test, whether this works or not. Personally, I like second derivative tests. Let's take the second derivative, and then we can determine whether we have maxes and mins. All right. So if I use a second derivative test, we'll have, let's see, 12x squared minus 6. All right. So there's my second derivative. If I plug these points in, as long as it's not 0, I can tell whether it's a maximum or a minimum. So let's start with 0. If I plug 0 in, I'm going to get negative 6. Well, we know by the second derivative test, since we got negative 6, this is going to be a maximum. Oh, we don't want that. That's not good. Hopefully, the square root of 3 over 2 is going to work. So if I have the square root of 3, so 12 times the square root of 3 over 2 squared minus 6. All right, when I square the square root of 3 halves, I'm just going to get 3 halves. So 12 times 3 halves minus 6. I'm going to get, let's see, 18 minus 6, which is 12, so a positive. We know from the second derivative test, if we get a positive number, this is going to be a minimum. All right? Same thing if I plug negative square root of 3 halves x. So I'm also going to have a positive 12, because when I square it, it's going to become positive anyway. So this is also a minimum. So we have two points, actually. In order to find the y value, all we do is we plug that back, these points, right into here. So to answer the question completely, I'd plug the square root of 3 halves into that equation, and we'd figure out our y value, and we can do it real quick. All right. So if I square 3 halves, I'm going to have just the square root of 3 halves. I'm just going to have 3 halves minus 4. So this is what, 8 halves. So I get y equal to 5 halves, no matter whether I put negative square root of 3 halves or positive square root of 3 halves, because I'm squaring it right here. It doesn't matter. So it looks like my points, my minimum distance, all right, my distance from 0, 2 to that graph is going to be the square root of 3 halves and then 5 halves and the negative square root of 3 halves and 5 halves. Both will produce the minimum distance from this point 0, 2 to y equal to 4 minus x squared.